Okay, so now we're going to look at velocity, and we're going to look at average velocity and instantaneous velocity, and then we'll do a few examples. Now, average velocity is defined a lot like the average speed was in the previous video. It is your total displacement over some total time interval, okay? And your instantaneous velocity has the same mathematical form, okay? It is delta x over delta t, but in this case, your delta t is very, very small. So imagine tracking something's motion, okay, an object that's moving, and looking at how far it moves in a very, very small time interval, okay? If you can track how far it moves in a very small time interval, that will be its instantaneous velocity. I like to think of instantaneous speed and velocity as the quantities that either your speedometer is giving you at a specific moment in time, or the value that a radar gun from, say, a police officer would give if he were to measure the speed of your car. Okay. Now, the velocity of your car is that number plus the direction that the car is moving in, okay, just to be clear. So let's do a quick example here, and we're going to find the average speed of this car. So we have a car traveling from x equals 0 meters, x initial is 0 meters, to xf is 400 meters, and in a time interval of 12.5 seconds. Now, what we want to do is get in the habit of drawing a diagram. Now, we can solve this problem without drawing a diagram, but we're going to draw a lot of diagrams, and it will never be a bad thing to get into the habit of doing so. And in drawing a diagram, we're also going to get in the habit of defining a coordinate system, okay? So let's draw a diagram, and we'll define our coordinate system. So I'm going to say that my initial position is here, and I'm going to say that my final position is here. Now, technically, positions can also be vectors because they have magnitude and a direction, okay? And we're going to define our coordinate system. And since our motion is only in one dimension, we really only need to worry about defining one-dimensional coordinate system. So I'm going to let that be the plus x direction, and I'm going to let that be the minus x direction. And at some generic point in the traveling, right, our car will be moving that way, okay? So now that we've got our picture, we know that the car started at this initial position, and it's going to finish at this position in a time interval of 12.5 seconds, and this displacement of 400 meters, okay? Now we're in a position to actually calculate what the average speed of this car is. So the average, okay, remember, is delta x over delta t, and remember what delta x means. Delta x is the change in, or the final minus the initial. So when I take the change in position, this is going to be my final position minus my initial position, and I'm going to divide that by the time interval. And so we're going to now plug in our numbers, and when we do so, we'll get 400 minus 0 meters over 12.5 seconds. And if you run that number, you'll find that the average is 32. Okay, so 32 meters per second is the average speed. Now, if you recall from the previous video, okay, 400 meters is 1/4 of 1,600 meters, which is very close to a mile. So this would be something like a quarter-mile drag race, okay? And 12.5 seconds is not an extremely fast car, but it's pretty fast. And so this this average speed is going to be somewhere around 67 or 68 miles per hour. Okay, maybe closer to 70 miles per hour. And of course, a good car is going to get well above that in a drag race. But the average speed for the whole race may have been 32 meters per second. Okay, so now let's do another example. And I want to go back to the racetrack idea, okay? I want to go back to the racetrack idea. Now, let's say that I have a oval track, right? Again, we're going to talk about quarter mile. So xi is going to be 0, and xf is going to be 400 meters, all right? So our runner is going to start here and run around the track, and we're going to assume that the instantaneous speed is constant throughout the whole track, okay? So we're going to assume that the instantaneous speed is constant throughout the whole track. And we will also assume that, let's say the time interval is 6 minutes, okay? So somebody is just jogging around the track, all right? Now, what is the average speed for this trip, okay? So if our runner starts here, what is the average speed around the track? And the way we can find this is if we assume that the average speed is constant, okay, then what that means is that each individual point along the track, they're going to be running with the same speed. Now, here's the kicker, okay? We know that xi, our initial position, is going to be 0 meters, xf is 400 meters, but in reality, their distance that they traveled is 400 meters. Since they ended up back at this spot, their xf is actually their starting point again. Okay? So in actuality, their ending point is 0 as well because they're ending right where they started, all right? And so you might be able to gain a little bit of insight now into where we're going with this. The average speed, or I'm sorry, the average velocity okay, is going to be 0 meters per second. And that's because their displacement is 0. When you end up right where you started, your total displacement is 0. That means your average velocity is 0. That can seem a little counterintuitive to a lot of people. Okay? Now, actually, I lied. Not only do we want to assume the average speed is constant, we want to assume the instantaneous speed is constant. So that means the person is running with the same speed around the entire track. Okay? So the instantaneous speed that they're running with is constant. Now, here's a trick from mathematics, and that is the speed, the direction that I am moving in is going to be tangent to the curve that I'm bound to, that my motion is bound by. So if my motion is bound by the oval here, as I'm running around the track at this particular point, if you think of my finger as the direction that I'm pointing in, as I'm running around the track, when I am crossing the start line, my speed is pointing in the direction to the right here. Okay, so this would be my instantaneous speed. And then as I run around the track, my instantaneous speed is at this point in the exact opposite direction. Okay? And as I'm running here, my instantaneous speed is pointing down. And here my instantaneous speed is pointing up. Okay? So those are actually your velocity vectors. okay? Because remember, velocity includes both direction and magnitude, okay? Magnitude and direction, I should say. So for every point that I have a velocity vector pointing downward, I have on the other side of the track another velocity vector pointing upward. And since I have a velocity vector pointing this way, I have another velocity vector pointing this way. So when I look at the instantaneous velocity vectors, these arrows around the track, I see that I have arrows that are pointing in exactly opposite directions on opposite sides of the track, and those arrows cancel each other out. That is why my average velocity is going to be 0 for the entire trip around the track, even though my average speed would be 400 meters divided by 6 minutes. Okay, so that is a one way in which the vector nature of velocity is extremely important. When we're talking about velocity, I have to take into account the direction. So, for example, if you're driving on the highway and a friend calls, you're on your way to a friend's house, and they call to get an estimated time of arrival, and they ask you, hey, what's your speed? And all you have to do is look down at your speedometer and say, I'm going 60 miles per hour or 70 miles per hour, whatever the case may be. But if they were to ask you what your velocity was, you would have to look down at both your speed and either a compass, or you would have to be able to know what direction you were traveling in. And then you would say, well, my velocity is 70 miles per hour northeast, or 70 miles per hour due north, or 70 miles per hour 30 degrees north of east, something of that nature. Any quantity that can allow you to give the direction is an allowed way to report a velocity, but you have to be able to report the direction as well. Now, before we close, let me introduce the idea of acceleration, and then we will flesh out acceleration in the next video. All right. So if we go back to the racetrack, all right, and the car racetrack. And so we had our car start here and end here. And when you're on a drag strip, right, if you're in a car on a drag strip, there's always one fundamental assumption, and that is your car starts from rest. So our velocity at the start line should be 0. And our final velocity would be something much larger than 0, right? In a really good car, you would probably be going over 100 miles an hour by the time you cross the finish line in a quarter mile. Now, so what that means is that my speed and my velocity don't necessarily have to be constant. So if my velocity is not constant, if my magnitude and direction is not constant, then that means that something else is also happening. Now, when you accelerate in your car, you feel it because if you slam on your gas pedal, you feel thrown backwards against the seat, and if you slam on your brake pedal, you feel thrown forward against your steering wheel, right? So your body actually knows when it's accelerating. So what is the definition of acceleration? And we'll start with the average acceleration. Well, if velocity is the change in position over some time interval, your average acceleration is the change in the velocity you experience over some time interval. And your average velocity, okay, is going to be the total change in the velocity, while your instantaneous acceleration is going to be measured over an extremely small time interval. So if you can imagine looking at your initial speed and then a very short time later measuring your final, I should say your initial velocity, and a very short time later measuring your final velocity, then that will give you the acceleration you're experiencing at that particular instant in time. So in the next video, we will flesh out acceleration. All right, thanks.